All right, so we finished up last week with talking about correlation coefficients. If you recall, we talked about covariance, right? Covariance being kind of like our variance measure of the extent to which X and Y vary with one another, but covariance in and of itself not terribly intuitive in terms of a meaningful interpretation. But if we take that covariance divided by the product of standard deviation of Y and standard deviation of X, we get our correlation coefficient, right? Correlation coefficients ranging from -1 to 1, indicating magnitude of a relation between two variables. This is not news, but then we did talk about our correlation coefficient is not an unbiased estimate of the population coefficient, particularly in small samples. If we're working with small samples, talking about this adjusted R formula here and what that's going to do. If we're working with smaller samples, it's going to go through and it's going to shrink that coefficient down a bit. Okay. Talked about testing significance of our correlation coefficient, our null and our alternative hypotheses. Remember, when you're putting these together for your assignments, making sure that you're identifying what variables we're talking about and what the populations are going to be important there. And then what we find is that our correlation coefficients, sampling distribution of correlation coefficients, following a t distribution with n-2 degrees of freedom. This makes it nice because we don't have to have a whole new sampling distribution to test statistical significance. We're just going to use our t distribution that we know and love. Makes it easy. Specifically, to get our test statistic for testing our correlation coefficient on whether or not it's reliably different from 0, we're just going to take our correlation coefficient, multiply that by the square root of n-2, and take that over the square root of 1 minus the square of our coefficient. Gives us a t statistic that we evaluate on n-2 degrees of freedom. Easy peasy, right? Also talk about R in and of itself being an effect size, very basic form of effect. And this is oftentimes what we'll see in meta-analyses. Effect sizes from different studies being converted to an R metric, and then being able to compare those, small, medium, and large. For R's, straightforward relation between D and R, right? Remember that our point biserial correlation, where we're looking at the relation between a dichotomous variable and a continuous outcome, is identical to our t-test, right? The p-value you get for a point biserial correlation is going to be the exact same p-value you get if you were to run that test in a between subjects t-test, right? They're the exact same thing. They're not telling us anything differently statistically. Our t-test is just taking this approach as a means-based test. Our point biserial correlation is just looking at the association between the two variables. But functionally, it's the same thing. We're just talking about it a little bit differently, right? And so what we can do then, if someone's looked at the correlation between gender and extroversion, and they give us an R coefficient for that, what we could do is we could translate that R coefficient into a D, and then interpret that in terms of standard deviation differences across the two means. Or if we get someone who's reported a t-test, the difference in extroversion across men and women, and give us that effect size in a D metric, and we want to just look at that in terms of correlations with other things, we can turn that back into a correlation and move easily back and forth. Remember from that first lecture that we went through, talking about taking the GLM approach, a Pearson correlation being exactly the same thing, or excuse me, a Pearson correlation being equivalent to point biserial correlation, which is the same thing as a t-test, right? And so all these things kind of working together. It just depends on how you want to communicate this, and then choosing the appropriate coefficient there. Okay. Also talked about our R squared statistic. So our R is just, our Pearson correlation is just a metric of the strength of an association between X and Y, right? And again, this is a test statistic that's representative of a population correlation, that's a hypothetical value, right? We don't ever know, but as our sample size starts to get increasingly large, we're assuming that this R coefficient is going to start becoming increasingly close to, we indicate this with rho, right, at the population level. Now our R squared value, if we take this Pearson correlation and square it, what that does is that translates that into a proportion of variability, right? So if I will go through and say my medium effect and square that, I get an R squared of 0.09. That's telling me that 9% of the variability in whatever my Y variable is accounted for or shared with, accounted for means like this, sounds like there's a causal relationship there, but 9% of the variability in Y is shared with X, right? If we want to get very precise. I mean, I'm fine if you guys are saying the variability in X accounts for 9% of the variability in Y. We're just talking about shared variability when we take that coefficient and we square it, okay? And so at the bivariate level, now we can do this with R. We can't do this with our regression coefficients that we'll get into. Sometimes you see people doing that. Would advise you not to do that because those are different types of coefficients. But for a straight up Pearson correlation, you can just square that, and that's why if we go through and we calculate a point by serial correlation between gender and extroversion, and we say get a correlation of 0.3, we're saying that gender has a medium relation with extroversion, and we could square that, and then we could say gender accounts for about 9% of the variability in extroversion, right? And so that's a different way of talking about that relationship, as opposed to saying there's sort of women score or a half standard deviation higher on average in extroversion than men, right? It's all interchangeable. It's all the same thing, right? You just want to determine what's the best way that you want to go through and communicate information with other people, right? I went to the mat with a co-author one time about, I had a demographics table, and I was just trying to sort of talk about the relation between two things, and every other thing on there was talking about a relation between X and Y, and then I didn't want to switch over and start talking about differences across gender as mean differences, so I said, just give me the correlation between that. And like, oh, you can't do that. And I had to say, no, I assure you, I can. It's all the same thing, right? It doesn't matter. It's fine. Please just give me what I've asked for here, right? And so sometimes people will get all up in arms, but it's statistically, mathematically the exact same thing, right? So if you run a t-test between gender on some outcome and you run a correlation on it, the p-values will be identical. If they're not, you've done something wrong in terms of calculating those things. Okay. Questions on any of this? All right. Assumptions. Did we work through this? No. Okay. Assumptions of our correlation. So if we're going to draw inferences about our correlation coefficient as an estimation of the population association rho, we're assuming that the joint distribution of X and Y are following what we're going to call a bivariate normal distribution. Okay, this is where we have to get into three-dimensional thinking here. So everybody look at me. Do this. All right, this is your X and your Y axes, right? Throw that middle finger out there. Do that, right? This is your Z axis, right? And if you turn that around and look at that, we've got a three-dimensional space right here, right? This is what we're looking. If we get into 4 dimensions, then things start to get weird, so we won't worry about that. But if we're talking about three-dimensional space right here, think about this as a surface where we're assuming a conditional distribution of X and Y, right? So that we're of X, and a conditional distribution of X on Y, such that the distribution for X values for any individual Y value of Y is going to be normal. And so if we take a line and bisect sort of this three-dimensional plot here, and we look at that cross-section, what we're going to see is for values of Y equal -1, we get a normal distribution of X's. If we were to cross-section and look at Y equals 0, we're going to see a normal distribution. If we cross-sex it for y equals 2, we're going to see a normal distribution, right? And so think about this as if we took infinitely small, thin slices of x for each value of y, we would see this normal distribution, okay? Are people kind of seeing this, being able to visualize this okay? So we're assuming a conditional distribution of x on y, and so the distribution of y value, or excuse me, y value, we're also, conditional distribution of x and y, meaning that the distribution of x for any y is normal, and the distribution of any of y for any x is also normal. Okay, that means if we look at an x value and we look at the y distribution here, y is still normal. And the same thing. So just as we did before, if we went and looked at for x values of 1 and ran a cross distribution here, we'd see a normal distribution. For x equals -2, we'd see a normal distribution, right? So in a bivariate normal distribution, we're assuming for any given value of y, the x's that correspond to that y have a normal distribution. For any value of x, corresponding y values, for anybody who has that value of x, those are also normal. Okay? And so what we see here also is we're assuming that the marginal distribution of x and y is normal. And so that if we just look at all the y's have a normal distribution. If we look at the x's, all the x's have a normal distribution. Okay? So this is just the marginal distribution. This is just our univariate distributions of these variables, right? This is what we've been dealing with previously. If we look at x, x is normally distributed, y has a normal distribution. And then if we think about our conditional distribution, this is saying if I sort my data and I look at everybody who has a value of y equals 50, and I look at the distribution of x scores for everyone who has y equals 50, Katie, what should the distribution of those x values be? Normal. And the same thing for everybody with x value of 100 and x value of 10, so on and so forth. Okay. Questions about this? Okay. So this is, you notice some little asterisks here, and we're going to get this into when we get into regression. The assumption of correlation is that we have a bivariate normal distribution. The distribution of x values for any y is normal. Distribution of y values for any x is normal. But this is only for correlation. As soon as we jump into a regression, we're not assuming that the distribution of y values for any x is normal. That's not an assumption of regression models, but it is for our correlations. Now, when we get into regressions, this is not a formal assumption of regression models, but it ends up being a functional, but it ends up being an assumption because we violated something else. And if we violate a different assumption, but we still meet this assumption here, then everything turns out to work out okay. Okay. But for the purposes of correlation, you want to know that the conditional distributions of x and y are both normal. Okay. You sort of comfortable with three-dimensional thinking in this manner? Okay. So what would be the shape of a bivariate normal distribution under the null hypotheses? So if x and y have no relation at all, what's the bivariate normal distribution going to look like? Any ideas? Yeah. So if x and y, if the relation between x and y is truly 0, what would this bivariate normal distribution look like? Would it look like this, or would it look something a little bit different? What's that? What's that?
Flat. I'm just guessing. I have no idea.
Not quite flat, right? Because we're still assuming sort of normal distributions, conditional normal distributions. How might that differ from this one here? Stephanie, I think you're thinking about it. What are you thinking?
I'm thinking privately.
You're not. You're by definition not, because otherwise I couldn't have.
I was thinking that it might look bimodal or it might be skewed, but they wouldn't like it wouldn't be that neat anymore. Like we wouldn't see normality on both planes.
close, except the exact opposite, right? We're seeing here that this is kind of looks like an anthill that's kind of stretched out, kind of long. If this were truly no effect, what we'd see is just a nice anthill, sort of each way, sort of everything's a nice kind of circular anthill, right? Do you see what I'm saying, Sam, with this? All right, because X isn't related here. Well, you also your nonverbals were telling you, so maybe a light was coming on here, right? But see, so we can see that we do have a relation between X and Y because we've kind of got this thin sort of distribution. If we cut it this way and that way, we're still bivariate normal, but it's kind of pulled out. If there's no relation between X and Y, it just sort of goes out sort of uniformly everywhere, right? So it doesn't matter which way. There's no relation between X and Y here.
Like a dome?
What's that?
Like a dome on the plane?
Kind of like a dome on the plane, except more it would sort of get sort of closer to if it's truly normal, right? So if you take, so if you were to take sort of that and just revolve it 360 degrees.
So normal dome.
Yeah, it would be a normal dome. Not so,
Like a
we have a-
three-dimensional.
or a negative a platykurtic thing, not like that. But yes, like this, if we just took that and sort of turned that 360 degrees around, this would be the exact same distribution any way we cut the pie, right?
If you could stand under it, and it would be like,
Mhm.
you'd be in a circle.
Yeah, with kind of a sloping up normal towards the top. Okay, and so do you see how that differs than what we have here? This is kind of sort of thin and sort of demonstrating a curve here. So again, helping to think about as we start talking and we're working in multivariate space. Again, we're kind of limited to two predictors and a y value. Outside of that, we sort of get into time dimensions and things, which is difficult to think about. But people sort of understand this idea of conditional distributions of X and Y.
So that happens when they have zero relation?
Yeah, if X and Y are unrelated, it's just kind of a perfectly symmetrical dome sort of normal thing everywhere. If we have here, this graph would suggest that we do have a relation between X and Y based on sort of how this is all played out. All right. Pretty straightforward in terms of basic assumptions of our inferences from our correlation coefficient. Okay. Questions on this before we move on? Okay. So some different things that we can do with our correlation coefficients, and I would encourage you to take a look through the Howell chapter that's assigned to help sort of solidify some of this stuff. But what we can do with our correlations is we can go through and we can compare independent correlation coefficients. Okay. And our null hypothesis here is that the difference in population coefficients is 0. P1 is equal to P2. Here, difference in population coefficients is some non-zero value, it's something different. Okay. Someone give me an idea for where we might compare two different independent coefficients.
If I wanted to know whether the association between two variables for an African American group and a Latino group are comparable.
Perfect, right. I'm interested in looking at the relation between, let's say, social support and acculturation or something like that in this immigrant group and that immigrant group, right? We're working with the same variables, right? We're still working with the same X and Y, but we're working with different populations, right? And so I might see that for one group, the correlation between X and Y is 0.4, and another group, it's 0.25. And what I want to do, I'm measuring the same variables, but what I want to do is see whether or not I have evidence that my estimated population correlation is stronger for this group versus that group. Excellent. That's exactly what we're going to do here. Now the problem is that the distribution of R1 minus R2 starts to get complicated, right? It doesn't follow a nice clean distribution that we can sort of know and then test against. And so what we do in order to perform a calculation like this is we take our coefficients and we transform them using what we call Fisher's R to Z transform. Basically, we take our correlation coefficient and transform it into a Z-score using this formula. Now, we're not going to call this Z because it's not really a Z per se. We'll call this in my one group and turn it into R prime. I'm going to take 0.5 times the natural log of 1 plus my coefficient over 1 minus my coefficient, that absolute value, okay? And that's going to give me R prime for my first correlation. I'm going to do the same thing for my second correlation. And then what I can do is once I've got my R prime, now I have something that is following a standard distribution that I can work with. And so I can calculate a standard error for R prime by taking 1 over the square root of the number of people in the sample divided by 3. Okay. And so then what I can do is I can go through and I can calculate a Z statistic by taking my R prime, so not, and subtracting that R prime 1 minus R prime 2. So the Fisher R to Z for my first correlation, subtract that from my Fisher R to Z for my second correlation, and divide all this by 1 over basically the standard error for R prime 1 over R prime 2. That gives me the standard error for these two things. Okay. Does this formula kind of look similar to something we've done before? Kind of looks like a t-test formula, right? Where we have not just one standard error, but we've got error associated with this group and that group, right? And if we go through and run this, we end up with a Z statistic, and then we test that Z against critical value at whatever alpha we're working with. Okay. So what we want to do is we want to compare correlation in this population and correlation in that population. We can't compare the correlations directly because that distribution is complicated. So what we do, take that correlation coefficient, transform it in a Fisher using our Fisher's R to Z, so we get R prime. So we get R prime for group 1, R prime for group 2, and then we can take those R primes, compare those, calculate a Z statistic that we can then base an inferential test on. Okay. People comfortable with this process? Kind of see what we're doing here? Okay. So this is if we're comparing independent coefficients. Okay. What we can also do is we can also test our correlation coefficients against a hypothesized value. What's the hypothesized value we're generally testing our correlation coefficients against? 0, right? Is this value, do we have sufficient evidence to support the claim that this value is something different than 0, right? That's what we always do. But it's not hard to imagine a situation where I might think that I could probably come up with a more interesting hypothesis than these things are orthogonal with one another, right? And so what we can do, and if you think about back on some of those meal articles that we talked about, right? Sort of this paradox between social sciences and hard sciences is not that sort of as our methods become increasingly more sophisticated, saying that, hey, X and Y aren't related, and as our tests start to become more and more powerful, that actually is a less stringent test as opposed to a more stringent test, right? Because we're just saying that X and Y aren't related. Is the relation between X and Y in the population always going to be exactly 0? No, it's kind of a ridiculous hypothesis to begin with, right? And so this is where they're talking about in the hard sciences, it's not, is this different than 0? It's, is this value, right? So this is starting to get something a little bit closer into saying, so I'm going through and I'm saying, and I'm looking at the relation between X and Y in this study that I've gotten, right? And I know based on previous literature that if I've done this right, that correlation between X and Y shouldn't be 0, it should be somewhere at least a minimum of, say, 0.2, right? What we can do is we can test that hypothesis using similar methods. So my hypothesis here is population value is equal to 0.2, or the population value is not equal to 0.2, and actually test that. 0 doesn't have to be our reference point. Now, Howell questions the utility of this procedure because essentially we're calling our shot, right? You need to have some value that you're going to test that correlation coefficient against, but with increasing emphasis on meta-analyses and things like that, I mean, we're starting to get to a point in some of these literatures where we should probably know about where our stuff should turn out to, right? It should be about this level. And what we could do if we were being very sophisticated, we could start to test hypotheses on whether or not our associations that we're observing is exceeding some minimum point that would suggest a study failure. Way to do this, again, pretty straightforward. Testing this on a z-test. We're going to take our correlation that we're interested in. We're going to translate that into using a Fisher's R to Z, create R prime, subtract that from rho prime, right? This is just whatever we're testing against, the population value that we've set as our hypothesis. We're just going to take that value and R to Z that back and call that, create that. So if I had my correlation coefficient was 0.5 and I'm testing it against population value 0.2, what I would do is take my 0.5, Fisher R to Z that to get R prime there, take my hypothesized value, which is 0.2, take 0.2, R to Z that into a rho prime, and then divide that over 1 over n minus 3. Okay? What does this formula look like? We talked about last semester. What do you think, Angela?
Well, in the formula, it would have just been X over because we would have assumed the population was 0.
Right. So thinking about some of the means-based tests that we worked with last semester, what does this formula look like? The last one looked like the independent sample t-test. What does this one look like? Single sample t-test, right? It's the same type of thing, right? A single sample t, we're comparing some observed value with some point estimate, right? We're doing the same thing here. You can see that this starts to look in function very similar to the single sample test. This looks in form very similar to our paired sample test, right? So again, starting to make connections between these tests and thinking about, oh, I mean, it's not a means-based test, but it's kind of the same, sort of similar in many aspects, okay? People seeing sort of what we've got going on here is sort of the type of test that this might come up against. All right. And then the last one we're going to talk about, comparing correlated correlation coefficients. Okay. Someone tell me where this might come into play. What's that?
Is this within a single individual?
Not within a single individual. What's that? Okay, within a single sample, right? So what are we looking at in this single sample?
Maybe 2 different measures of the same.
Okay, maybe, right?
I'm like thinking of one of the articles talked about, like, if you're looking at 2 different intelligence tests,
Mhm.
and trying to fit in, there's like a longer version and a shorter version, and you're looking to see if they're equally correlated with the outcome.
Okay,
I
right.
don't know if that's a different thing.
Kind of, we're talking about the same thing. So I have a paper under review right now looking at sort of whether or not different aspects of PTSD are conforming to sort of some theoretical stuff. And people familiar with tripartite theory of things? Okay, so there's this idea that mood and anxiety disorders have a unique and a general component, right? We have positive affect, negative affect, and then like anxious arousal types of stuff. And so maybe I'm interested in sort of, let's say, this piece of PTSD, based on theory, should have a stronger correlation with anxious arousal than positive affect. Okay, so I've got 3 variables. I've got my PTSD variable, I've got positive affect, and I've got negative affect, or anxious arousal, right? And so what I want to know is whether or not the relation between PTSD and anxious arousal is stronger than the relation between PTSD and positive affect, okay? Now, why are we calling these correlated correlation coefficients? What do you think, Katie?
Is it because you expect some shared variance between PTSD and the interest?
Yeah, so I'm expecting some shared variance, but I've got a common measure in here, right? So X is in both of these, right? Before, we were talking about the relation between X and Y in this population and X and Y in this population. Here, what we're saying is within sort of this population, X has a stronger relation with this variable than X has a stronger relation with that variable. So X is the common measure in both of these correlations, and so the correlations aren't independent of one another. I mean, they might be, but there's going to be some level of share there. We have to take some additional stuff into consideration, right? And so what we're doing is we're saying within the population, the relation between X and Y is sort of different than the relation between X and Z. And the way we set this up, we'd say the relation between X and Y, subtract the relation in X and Z equals 0, because if they're the same, they're going to be 0 or something very close. Our alternate hypothesis being that correlation in X and Y, if we subtract correlation in X and Z, is going to be some non-zero value, right? So that we've got different correlation coefficients. This starts to become a more involved process. You've got a couple of readings that talk about how to go through and calculate this out. There's a number of different correlations that you have to take into consideration and tie this together. I'll let you guys work on that on your own. But what's interesting here is that what we can also do, and so this is outlined in a couple of different readings, looking at correlations and starting to make specific contrasts, and also if we're talking about repeated measures, we can also use this same procedure to say, is the relation between my measurement at time 1 and time 2 the same as my measurement at time 1 and time 3, right? Or is time 1 and time 2 the same as time 2 and time 3? Starting to work on, work with some repeated measures stuff in this, okay? And so again, some procedures outlined. How Steyer is an old paper I didn't recommend, or I didn't assign, but you could go through and look at that. This Meng et al. 1992 is similar. And so there's some opportunities to go through and take a look at that for this next assignment. Yeah, Morgan.
Can I ask real quick, just so that I'm writing properly? Can you explain with the example of your paper again, just so that I can figure out, make sure that I have a common measure rate?
So let's say,
I'm not going to steal your research.
that's fine. Good luck trying to publish that paper. I haven't had any. So if I'm looking at the correlation of PTSD and anxious arousal, and I'm saying that that should be greater than the correlation between PTSD and positive affect, right? Because theoretically, this construct, this PTSD construct, should have a stronger correlate, be more strongly related to core features of anxiety than it has with core features of depression. So if we're saying anxious arousal is a core feature, a unique feature of anxiety, and low positive affect is a unique feature of depression, this PTSD construct, or this piece of PTSD that we think is very anxiety driven, it should be more strongly related to core features of anxiety than it is the core features of depression, right? And so we've got 3 variables here. So we've got X1, PTSD, X2 is anxious arousal, and X3 is positive affect, low positive affect, right? How many bivariate correlations do we have right here? What do you think, Alex? How many correlations can we get out of that? Out of these three variables? How many different combinations can we have of three things? Three. So we can have the relation between x1 and x2, x1 and x3, and x2 and x3, right? So I'm interested in the relation of x1 and x2 and x1 and x3, but when I'm calculating this test, I need to know how x2 and x3 are related to one another, because depending on whether or not x2 and x3 have a very weak correlation or very strong correlation, that's going to start to influence the test of the correlation between 1 and 3 and 1 and 2. Okay? And so Meng does a nice job of walking through some pretty interesting things you can do. One, running these tests, but then also running individual contrasts for combinations of different variables and things along those lines, starting to turn this into sort of something you think about as kind of like a one-way ANOVA, except using correlation coefficients. So again, this isn't something we see often in the literature, but it's something that you could do if you had occasion to do it in interesting hypotheses that would fall along those lines. Questions on any of this? All right, cool. So what if we want to calculate confidence intervals for our effect size R? Okay, because we can calculate a standard error for R prime, what we can then do is use the standard error on R prime to now calculate a confidence interval around this correlation coefficient. So I'm saying that the relation between X and Y in the population is 0.4. Do we know, do we think it's exactly 0.4? No, 0.4 is still our best guess, right? But we're probably going to say there's some error there, so it could be a little lower, it could be a little higher, right? And so what we can then do, because R is an effect size, if we calculate a confidence interval around R, I'm calculating confidence interval around the point estimate of our estimate of association, but because R is also an effect size, we're functionally calculating confidence interval around an effect size here, okay? So what we're gonna do, formula here, is we're gonna take the confidence interval around rho prime, or our population coefficient, is gonna be our R prime, right? So our R to Z transform that we've created, plus or minus whatever our value is in terms of our confidence level. So if we want it, and so it's a sort of two-tailed test, right? So if we want this to be a 95% confidence interval, what's our Z we're going to use? What do you think, Sam? What Z value corresponds to 0.05? 1.96, right? So if it's a 95% confidence interval, it's 1.96. If it's 99, it's 258. If it's 99.9, it's 3.29, right? So we're going to use our critical value here multiplied by 1 over n minus 3, okay? Now the tricky thing here, okay, is that what this is going to do is it's going to give us a confidence interval, and it's going to give us a lower bound estimate of rho prime and an upper bound estimate of rho prime. Is this what we want? No. Why are you shaking your head, Maureen? Why don't we want rho prime?
Because we don't want it prime.
We don't want it prime, right? Like, so what we've created a confidence interval around a metric that isn't the correlation coefficient that we want. But because we know that there's a direct relation between rho prime and rho, or R and R prime, what we can then do is, once we've calculated the confidence interval around our Fisher R to Z transform, what we can do is then take the upper and lower limit, back translate that into a correlation coefficient, and then we've got our point estimate and our upper and lower values around that correlation coefficient. So if I want to work backwards from my Fisher R to Z, right, so my R prime, and work backwards, I take base E to 2 times R prime minus 1, and take that divided by base E times 2 times rho prime plus 1. So to go back through, that's going to back translate our Fisher R to Z transform into correlation coefficients, and then we just plug that in the upper and lower values there. Yeah.
Do you mean BC to row prime or R prime?
Well, rho and R, it's the same thing.
Oh,
It's
yeah.
thinking about like means and mu's and
Yeah.
things like that, right? So R is the same thing as rho. It's the same thing. It's rho is just what we're working with here. So we're assuming that sort of our upper and lower, our rho here is a correlation coefficient, right? We're just sort of treating this as our population estimate as opposed to sort of for this sample, this is the thing that we're getting, okay? So if you see rho is the same thing as R. It's the same thing as sample mean versus mu, you know, when we're working means-based stuff. Okay. So again, we went through Fisher R and Z to get it from our R value into our Fisher R to Z, our standardized R, our R prime. What we're going to do is then calculate our confidence interval around R prime or rho prime, and then we just need to take it back into the sort of metric that we actually wanted in using the formula right here. Okay. Actually, kind of pretty straightforward once you sit down. This is going to be one of those things when you sit down and start working with it, your sort of light's going to go on and be like, okay, I see, we're just sort of transforming this back and forth. Not all that different than, remember when we were calculating confidence intervals around D, we would calculate confidence intervals around our non-centrality parameters and then just back transform those into the D metric that we were actually interested in using. Same thing like here, except instead of non-centrality parameters, we're just using this Fisher R to Z. People okay with this? Cool. All right, power analyses for our Pearson coefficient. This is pretty easy, straightforward in G-Power. What we're going to do is we're going to, under test family, we're going to choose exact. Under statistical tests, we're going to say correlation bivariate normal model. For our test, we're going to say a priori sample here. Make sure that we're clicking a two-tailed test. We're going to determine a correlation that we're interested in testing. So in this case, we want to see how many people should we have in our sample to reliably identify statistical significance that the population value is 0.3. Okay, so you're saying I'm planning a study, I'm expecting X and Y to demonstrate a correlation of 0.3. How many people should I have in my sample over 80 of 100 replications to be able to detect, if that's the actual population coefficient, to get a sample large enough so I sort of identify that 8 times out of 10, or 80% of the time based on my power. Okay, and so then we go through and do that. So if we're looking to detect a correlation of 0.3, which is going to be a medium effect, right? If we want to detect a medium correlation in our study powered at 0.80, we need to have about 84 people in our sample in order to reliably detect a population correlation of 0.30, which is a medium correlation at at power equal 0.08 or 0.80. Does that mean that if I have 84% or 84 people in my sample, that I'm guaranteed to find a statistically reliable correlation to an X and Y? What do you think, Lauren?
Nice.
It would be nice, it would, right? But that's not going to happen. Why is that?
Because you're basically saying that it's going to be, you're going to find a result when the result isn't guaranteed. I don't really know how to explain it, but.
Okay. Remember, if we're thinking about, this is my population correlation is 0.30, right? And I grab samples of 84. Is every single one of those samples going to have a correlation, a demonstrated correlation of 0.30 between X and Y? No, right? We're going to get a distribution of correlations, right? Most of them are going to be something that's pretty close to 3.0, right? But we're going to have some that are down here that are going to give us correlations that are way too small, and we're probably not going to detect statistical significance. We're going to get a sample that tells us, even if the population correlation is 0.3, when we grab that sample 84, some percentage of them is going to tell us that we have a correlation of 0.1, right? It's not a good estimate, but we don't know that unless we do this over and over and over again, right? And so sometimes we're going to miss, but also sometimes we're going to get correlations of 0.6, which aren't real. Those are way too big, right? They're just at so the more convenient end of the distribution, right? And so again, we're saying that at 80 times out of 100, if the population correlation is 0.3, right? If that's that real value that we can never see out there in the universe, if this is the actual correlation, if we have samples of 84, about 80% of the time we're going to be able to find a correlation that we're going to claim is statistically significant. The rest of the other 20% of the time we're going to have something that ends up being too small, and we're going to fail to claim statistical significance. Okay. So just as a refresher for power, stuff like that, this sort of rekindling sort of knowledge centers in your brain. Yeah. We'll take your science as an affirmative. All right. I want to go into talk about point by zero correlation. Point by zero correlation tested the relation between, remember, a dichotomous X and a continuous outcome Y. Okay? So if I have a truly dichotomous variable, I want to look at the relation between this dichotomous variable and my continuous outcome. I'm going to be technically calculating point by serial correlation. Okay. Point by serial correlation, mathematically equivalent to a Pearson correlation. They're the same thing. They're interchangeable. You're not going to get, if I'm looking at the difference between, or the relation between gender and extroversion, and I calculate a point by serial correlation, I'm not going to get a different value if I calculate a Pearson correlation. It's identical, it's interchangeable, it's all the same thing. Okay? So for example, what I've got here from data that we've collected, people who've been in car accidents, do they have chronic pain, do they not have chronic pain? Here are the people with no chronic pain, here are the people who do have chronic pain, and this is PTSD score, right? And so the relation between chronic pain and PTSD severity is about 0.38, right? This is an ugly scatter plot, but basically what we're doing is drawing a line through the mean CAP score for people with no pain, going to the mean CAP score for people with pain. That's what this line represents. So we could talk about this in terms of mean differences, right? We could say that on average, people with chronic pain are reporting higher levels of post-traumatic stress disorder than people with low chronic pain, right? And we can talk about that in terms of mean differences. Or we can just think about this in GLM terms and say, what's the relation between chronic pain status and PTSD severity? And we can calculate a point by serial. It's the exact same thing. Okay, it's just how we want to talk about it. And this point by serial correlation is that identical to a Pearson correlation mathematically, and so everything kind of works out well. So when X is 0, our expected value of our outcome is the mean value here. Same thing when X is 1, our expected mean value is the mean of that group here in terms of this association. And here, if we square that point by serial correlation, just like Pearson correlation, this is still going to represent the proportion of variability in our outcome that's attributable to our grouping factor. So here, if we take 0.379 and square it, we get about 0.14. So we could say 14% of the variability in PTSD severity is shared with chronic pain status in this population, right? Now again, a lot of this is just based on how we want to talk about it. For means-based stuff, for comparisons, oftentimes, I mean, even though we can do this, sometimes it's often easier for us to think about this as just in terms of like mean level differences, but we don't have to, right? And as soon as we start running regression analyses with dichotomous variables in there, it starts to just be more efficient to start thinking about this in terms of relations, in terms of mean differences. But again, what I want you all to be able to do is think flexibly about this and be able to move back and forth between these and recognizing that it's all going to be all indicating the same thing. Okay. Questions about this? Okay, so point biserial, we've got a dichotomous predictor and a continuous outcome. Okay. Calculating the significance of a point biserial, same thing as we did before with a Pearson correlation. Formula is the same thing, we're just plugging in our point biserial correlation into our formula. We're still evaluating the test statistic against a t-distribution with n-2 degrees of freedom. Exact same thing. There's nothing different going on. There's nothing that you change. It's just your point biserial correlation is going in there. And the only thing that makes that a point biserial correlation is the fact that one of your variables is dichotomous. Okay. Again, looking at the relation between our point biserial correlation, mathematical relation to our independent sample t-test, which makes sense because it's basically functionally the same thing. If we wanted to calculate, if we had a t-test, right, and we wanted to see the proportion of variability, let's say I ran a t-test and I said people with accident-related chronic pain have higher levels of PTSD severity than survivors without chronic pain. And in my head, I wanted to be like, well, I wonder what proportion of variability is shared across here. I can do that easy. I can just take my test statistic, square it, divide it by the test statistic plus degrees of freedom. That gives me, this is my squared point biserial correlation. Okay. And so again, we just move them back and forth between tests flexibly to enhance whatever interpretation, however we want to present this. Okay. So again, interpretation of mean-based tests and our point biserials are interchangeable. We can talk about our point biserial correlation. If I get a significant point biserial correlation, I could say men and women are different in weight, okay? And that would be perfectly fine. I could also say gender is related to weight, and that's fine. Just however I want to talk about it. We could say there exists a linear relation between gender and weight. Physical weight varies with gender. We can start to get sort of communicate things in a way that's going to mean the most to our audience, and sort of moving back and forth with this. Okay. Questions about what we're doing here with our point biserial? Okay. Our effect size with point biserial, direct relation with D. If I have point biserial and I want to calculate a D with it, that's my formula, right? If I'm looking in an article that I'm reading and someone's run a correlation coefficient between a dichotomous predictor and a continuous outcome, and I've got another study or my study where I ran a t-test and I have an effect size, and I want to see how their relation corresponds to the effect size that I've calculated in my study, easy. I can just go do that. If I take that correlation, I can translate that into a D and then compare equal metrics with what I've got on hand. Right, if I've got one study that's reported a correlation, another that's reported an effect size, I can make those two things equivalent, right? This is super, super helpful. These types of things are really helpful in evaluating research out there because, unfortunately, researchers don't always provide us with the numbers that we'd like. But if we're savvy, we can go through and start getting numbers that we want out of the stuff that's provided. Okay. Again, confidence for our D then can begin derived using our point biserial correlation. So someone could run a correlation between gender and extroversion. And what I can do, based on my knowledge, I can take that correlation, and if they give me the test statistic that they actually used to determine that, I can then work backwards and create a confidence interval around D based on just this one correlation that I was provided, because I've got enough information that I can work backwards and do this. And this is just all the stuff that we've talked about last semester. Okay. People seeing how these are connecting, how we can sort of work forward and backwards based on the information that we have available to us. Cool. All right. Any questions with point biserial? Okay. Point biserial looks identical. You would never be able to tell the difference between a point biserial and a Pearson correlation. It's just that we're just calculating a correlation where one of our variables is dichotomous and the other is continuous. Okay. P coefficient, Phi coefficient is our formal test of the relation between a dichotomous X and a dichotomous Y. Phi also mathematically equivalent to Pearson R. It's just a different form of Pearson R. Looks identical, it looks exactly the same. Just in this case, we're having a dichotomous X, a dichotomous Y. We're going to go through and calculate a Phi coefficient. What else could we calculate if we want to test dependency between X and Y? What do you think, Sam? Nunez Lab loves these.
Oh, regressions.
Huh?
Regression.
Well, you guys love regressions. Chi-square, right? We're just looking at dichotomous X, dichotomous Y. It's chi-square. Same thing as Phi coefficient. Same thing as correlation. All interchangeable under. They're all just different expressions of the GLM here, right? Sampling distribution for Phi, function of chi-square with 1 degree of freedom. Okay, and so so just as we had with our point biserial and R and T, or point biserial and T, we interpret our Phi coefficient and a 2 by 2 chi-square as interchangeable. They're the same thing, right? So if I get a Phi coefficient of 0.3, I can use this formula to translate that into a chi-square and back and forth and go through and test the statistical significance based on a chi-square with 1 degree of freedom. Okay? So everything that we just talked about in terms of point biserial, same thing with Phi and chi-square, exact same thing, right? So again, what we can say is we can talk about our Phi coefficient is the association between a dichotomous X and Y. We could also, if we're talking about chi-square, we could say this is a test of independence between dichotomous X, dichotomous Y. It's all the same thing. It all works interchangeably. Questions about Phi? And so you see Phi as used as an effect size for a 2 by 2 chi-square. I use this all the time. If I'm running 2 by 2 chi-square, this is the effect size that I write. And I've put it Phi because it's technically a Phi correlation or a Phi coefficient, but Phi is identical to R. It's all the same thing. Mathematically, it's identical. It's just a special case of R. People comfortable with this? Okay. Some other coefficients, and there's a handout that I stole from Steve Bieber in stats when I was an undergraduate here that was just very nice, that I kept and then stole for my own purposes, citing him at the bottom, but outlining a number of different coefficients. It's not in the ones that I handed you, it's on my courses. But some other coefficients that you want to be aware of because they may come in handy. If we're talking about a biserial correlation. Biserial correlation is going to be similar to a point biserial, except the only thing here is we're assuming that this dichotomous X has an underlying continuity, right? So if I have am looking at physical sex, and I'm decided that physical sex is a true categorical variable, right? It's sort of this group or that group, then a point biserial correlation would be appropriate. But if I'm looking at, say, diagnosis, right? People who have depression and don't, right? So we're saying it's categorical, but is that actually categorical, clinical folks? No, it's probably a continuum of severity. At some point we just say, well, here's the line, we're gonna call it you meet the criteria or you not, right? Or if we say, same if I say, are you confident or not confident that this person killed somebody? And you just give me 2 choices, right? You're putting me in one camp or the other, but there's probably some gray area in between there, right? And so in this case, it would mathematically and theoretically make more sense to calculate a biserial correlation, because even though I'm measured this as a dichotomous categorical variable, I'm assuming an underlying continuity, okay? Same thing for tetracorrelation, similar to Phi, but I'm assuming that the construct X and the construct Y both exist on a continuum, not on a dichotomous dichotomous level. Okay? Spearman-Rowe, this is taking a Pearson correlation and applying this to rank scores. Okay, and this starts to become important, really forces you to start thinking about how we're actually measuring variables, right? Someone give me an example of a ranked score. What do you think, Steph?
First, second, third, fourth place.
I've got, that's right. First and second highest might be 10-point different, and second and third might be 2-point different, but we've just ranked these up, right? So it's not a true continuous scale, right? If we wanted to run a correlation between ranked scores, technically we should probably be thinking about a Spearman-Rowe or a Kimball-Tao alternative to looking at a relation between ranked scores. A little bit better estimate, right? Chi-square test for linearity, ordered categorical data, right? We often just slap a chi-square onto categorical variables, but if I've got variables that actually have, they're not just categorical, I've kind of got like this one is bigger than this one is bigger than this one, or there's some linear type of progression. Important thing about using a different test that accounts for the linearity of scores as opposed to things just being truly nominal. And then this coefficient concordance, multiple raters, it starts to get into inter-rater reliability types of things that we can start to use. But a wide variety, and this isn't all of them, there's lots and lots and lots of different coefficients out there. What I would encourage you to do is, again, when you're thinking about, okay, I want to test this thing, sit down, think about what are my variables, how have I measured these variables, what's the underlying construct I'm trying to capture, how does my measurement relate to that construct, and then choosing a strategy based on that. Questions? Okay, what time is it? Is it intermission? Should we really do it? No? All right. This next piece is all matrix algebra stuff that I used to have everybody do, but then in sort of thinking about all the things that I wanted to do, sort of where matrix algebra ranked in sort of all the progression of things, matrix algebra kind of fell out of the picture in terms of importance. If you're interested in sort of how any of this stuff works, I would encourage you to go through and take a look at some of these things, but I'm not going to hold you responsible for matrix algebra stuff. So kind of up to you. We won't work on this, we won't worry about this today. We're just going to jump into screening because that's going to be more applicable to the things that you're going to do, but underlying sort of mathematical bases for a lot of the stuff that we do, this is kind of relevant and I wouldn't say interesting, but I guess that's an opinion, right? So we won't get into this right now. So let's take a break, come back, and we'll jump into screening stuff. Right. Data screening stuff. Oh yes, I forgot. This is my screening haiku. Haikus are fantastic.
We're on, yeah.
So look, that's quite a use of time, sort of finding statistics haikus. There are good ones out there. All right. So thinking about why do we screen data? We've talked about this last semester, but just to re-emphasize things, you should always, before you're running any type of analyses, do some type of preliminary screening, right? Now this can be, I don't always do this. I'm like, is this going to work out? I just kind of want to look at this type of thing, and sometimes I don't. But you should always, before you're putting any formal analyses together, making sure that you're meeting your basic assumptions of analyses. Why is this important? Like, what happens when we don't meet our statistical assumptions? What's that?
You can't draw accurate conclusions.
Exactly, right? So the whole system is predicated on this idea that our data are meeting these certain assumptions. Now, sometimes we can violate those assumptions and not a huge deal, but sometimes if we do, we lose confidence in any type of inference that we should be able to draw from this. And so always important to go through, take a look and make sure that our results aren't a function of some weird thing going on somewhere. I was like, looked at it wasn't a paper that no, it was a paper that I reviewed. It had a scatter plot of like fMRI data that looked something like that, and then a point out there. And they're like, look at this thing. I'm like, that's not a thing. That's a random set of data and an outlier that's causing that. The whole thing is based on this, right? And either one, you don't know that because you haven't been trained properly, or two, you do know that and you're trying to sneak it by me. I'm not impressed with either. No thank you, right? So always important to make sure that you're going through taking a look at your assumptions and also providing insight to the nuances of your data, right? Like, you will not learn more about your data than just doing a basic screening, right? It's going to tell you, so this is what I thought was going to happen, this is what actually did happen. You're going to start to give you some insights in thinking about sort of the potential impact your methodology may have on your outcomes that you're getting, which if you're finding this, there's probably other stuff out there that's finding this. Just going to give you a much deeper understanding and appreciation for your data. Also, when you roll into defenses, dissertation, theses defenses, there should be no one in that room that can ask you any question about your data that you don't already know, right? You should walk in there with confidence and say, go ahead, try it, see what happens, right? If you've gone through and taken a look at this stuff well. Also thinking about sort of developing additional ideas, right? So I found that when I did this, so this is kind of the response that I got. I've got, it looks like a subset here. It looks like a bimodal distribution. I got another group of people out here that are doing something a little bit different. What's going on with those people? Is this interesting? Is there something going weird with my manipulation? Who are these people? Maybe this is the next direction for research. And then thinking about the limitations of paradigms, right? So I've done this thing, right? This is, you know, Adam, for Adam's thesis, he had an anger manipulation, right? So we'd bring people in and have them think about sort of something that makes them angry. You're like, oh yeah, this should get you worked up. It's actually really kind of subtle, right? I've done film paradigms where I bring people in and show them something that sort of is like very clearly supposed to do this, and you get that effect, but it's very, very modest, right? And so thinking about, okay, like eliciting affect within the context of an experimental setting using like visual, audio visuals, stimuli, you can do it, but it's not super intense stuff, right? Sort of starting to think about potential impact that might have on our designs and our outcome, right? And so always wanting to go through and sort of run these types of analyses so you know what you're working with, you know where the landmines are, and so you can make your interpretations accordingly. Okay? So we're going to go through these things. A lot of this is going to be reviewed because we've already talked about this last semester. Accuracy and plausibility, number one thing, we always want to look at our data, particularly if we have other people entering our data. So the advent of online questionnaires and having sort of more digital entry sort of helps with this, because if people can only choose 1, 2, 3, 4, or 5, they can't write in 7. Or you don't have people who are entering data who make a keying entry and hit 33 when they should have hit 3, right? But we should always go through, make sure that our data are within range, and we coded variables appropriately, right? If you've got multiple semesters of data in semester 1, women are 0 and men are 1, and the second semester, men are 0 and women are 1, that's, if you run a study with a participant pool and find them the majority of your sample is identifying as men, that should key you in there's probably something wrong, right? So go back through, just because I have 0 is women and 1 is men, my SPSS set there, appropriate variable labels, do I have the expected number of classes? If I have groups 1, 2, 3, and 4, and I don't have any groups, right, or I have a group 0 in there for some cases, right, wanting to go through and figure out what's going on with stuff. Again, this is old hat to you all, but accuracy, I think this is the first time I've actually had my entire 5300 course be exactly the same thing people I had in 5060. Usually I have people sort of popping in at, in spring, and we got to get them all caught up to things we've been doing for the whole first semester. So you guys are on a good spot, because this is all again, old hat. We've been doing this for all of the fall, looking through categorical variables, continuous variables, popping all this stuff up. Okay. Questions about this? All right. Missingness. Wanting to attend to sort of seeing what we have missing in terms of our data, and then needing to think about what's going on in that missingness. What's the cause of missingness? What's the function of missingness? And that pattern or that mechanism of missingness often is sort of the crucial thing that we need to be thinking about, right? If we have missingness that's random, right? If we have just sometimes people had a hiccup or they didn't report one thing or failed to reply to this one item, kind of scattered at random, often talk about that as ignorable, okay? Yeah, it sort of reduces our power because we, particularly for the statistics that we're running here, we got to throw those people out, but in generally, it's not something that's going to bias our results. But if we have non-random missingness, if we have systematic missingness in our data, that's when we start to worry about impacts on inference, generalizability, things along those lines. Okay. A basic sort of general framework for thinking about missingness. And you picked up a handout there that's going to give you a more in-depth, detailed sort of overview of some of these concepts. But this is attributable to Little and Rubin, thinking about the mechanisms of missingness. If we have data that are completely random, okay, like there really is no rhyme and reason to the missingness, within this framework, we're going to call this missing completely at random, or MCAR, okay? MCAR means that the probability of the presence or absence on some outcome is independent of all variables, right? So it doesn't matter sort of what the value of my outcome variable is. It doesn't depend on any of my predictors. It doesn't actually isn't actually based on the value of Y itself. It's completely, totally at random. If that's the situation, we can identify that as MCAR. MCAR is pretty straightforward. This is what we sort of consistent with what we would think of as truly random missingness. We also have something that's called missing at random. Okay? Missing at random isn't completely random. There's a systematic missingness involved in the data, but if we have data that are MAR, okay, the probability of the presence or absence of some outcome variable is dependent on observed value of X. Okay, so as this X gets higher, Y starts to become more and more likely to be missing, right? But what we find is that our the likelihood or the probability of X being present or absent, unrelated to the actual value of Y after we control for X. So basically, if we've got something that's missing at random, missingness is accounted for by other variables in the model, right? So there is systematic missingness in Y, right, or sort of one of our variables. So we see that as Y, or as X gets larger, we see it more and more likely that Y starts to become missing, right? But because we have these X values, and we can determine that Y is missing because this X value is getting larger, if we account for that, after we sort of partial out sort of that piece of X, then we know why Y is missing. And then after we account for that, then if Y is missing, it's just kind of completely at random. We would say that these data are MAR. So I think in the example that you have, and this is pulled from one of your, here's the all for review if you want. So if we look at the second page of that missingness data, you see that under MAR, we've got blood pressure measurements in January, and then Y is blood pressure in February. Okay, we see that under the MAR condition, February readings represent those collected from patients with January readings less than 140, right? And so under MAR, those individuals who have lower blood pressure levels at the start, lower blood pressures in January are associated with missing this at in February. And so because missing this in February is a direct function of the value of scores that we had in January, we would say that these data are MAR, right? So it's not missing at random in the sense of complete random data, but we can account for the missingness. We know why these data are missing is because if someone had low blood pressure levels in January, then they weren't collected in February. And so even though those blood pressure values are missing, we know the mechanism of missing this. And so we would calculate, and so we would conceptualize that as missing at random. Okay? So it's not missing completely at random because it's not actually sort of the values of the missing values in February. If we're assuming that blood pressure in January and February are correlated with one another, what type of values are we missing in February? What do you think, Katie?
Those with January treatments that were less than.
Right. And so what, if we're looking at the sample of values that we do have in February, what's probably missing from those values? Who are we missing out on? People with lower, right? And so missing this in February is related to the value of the variable that's missing, right? Missing this in February is related to blood pressure in February because those with who would anticipate as having lower blood pressure are the ones who are missing, right? But we know that those values are missing based on the full data that we've got in X. And so even though there's systematic missingness in February, that systematic missingness is accounted for by values that we've collected in January. And so then we would call this missing at random, okay? Because in multivariate space, if I'm using an estimator like maximum likelihood, a full information method, I can still use these and still look at these data without too much bias because the missing values that I have are directly a function of this other thing that I do have. And so missingness is accounted by a different variable that I have in the data, and so I'm going to be okay here. So MCAR and MAR generally thought of as ignorable missingness. Missing not at random, however, probability of presence or an absence of a given value in Y is dependent on the actual value and the unobserved value of Y and probably X's as well. Okay. Now, if I were to collect variable or blood pressure in, if I were to collect blood pressure in February and didn't have access to January blood pressure, what type of missingness would I have then, Angeline? Missing not at random, right? Because I've got a sample of individuals who I'm missing blood pressure values, and the missing values are a function, they're a direct function of blood pressure, but I don't have these other values that accounts for it in my data set. And I might even say, yeah, I'm sort of missing people on the low end of blood pressure, but if I don't have any other measure of blood pressure in there, then I've just got missing not at random data, right? There's systematic missingness that's going on here. And so this is one of these things, one of my peeves in terms of treatment outcome research, right, is we use like hierarchical linear modeling and some of these types of analyses that use like maximum likelihood estimation, right? And we say this is better because we don't have to have full data for everybody. We can go through and just estimate sort of these change in outcomes based on the data that we have, right? But the estimator we're using is assuming that data are at least missing at random, right? Do people drop out of treatment for random reasons? Not for random reasons, right? And so what we're doing is even though mathematically it will account for these data, pattern of missing this, the mechanism of missing this probably isn't meeting the assumptions of the estimated that we're using, and so there's still going to be bias in those approaches, right? And so again, when we're thinking about when you're looking at your data, right, are there people in my set? Is there systematic missingness? Is there some thing that's going on? Or if I am missing data, is there something in my set that actually accounts for some of that stuff that's gone on? Okay. Questions about this? So go through, take a look at this sheet again, and I pulled this off of what's the hijacked this out of Schaefer and Graham. That's a really nice article to give you a good sense for mechanisms of missingness and potential impact and things like that. All right, questions on this? Okay, so missingness, wanted to take a sense, get a sense for that. Other thing we're going to think about what we just talked about at the beginning of the class, distributional assumptions. For multivariate analyses, what we're going to assume, in general, univariate normality of scores, okay? We want our scores for these correlational methods, individual distributions, observed distributions, to approximate some type of reasonable distribution, okay? Actually, what we're looking at is just something that's not severely non-normal, but the basic assumption is univariate normality. So if we look at individual variables within our model, we're hoping that those variables have some reasonable approximation of normality, or at least not severely non-normal. Okay. And then what we want to do then go, oh yeah.
Is this assumption of normality for our observed data or for the population?
Yeah, it's observed data, so we're going to get into distribution of sample means, stuff like that, when we start talking about group versus ungrouped. So you're going to have to be flexible, thinking about, okay, am I running a group analysis, like a MANOVA or a repeated measures ANOVA type of thing, or am I working with like a regression type model in terms of thinking about this? So here, for right now, think about univariate normality in our observed scores. Multivariate normality, similar to the bivariate normality that we had talked about before, but now we're jumping into fourth, fifth, sixth, seventh, eighth dimensions and so on, where the assumption is that each variable and all possible linear combination of variables are normally distributed. Okay? In the bivariate case, if it's just x and y, we've got our three-dimensional graph here that's pretty, that we can visualize, right? So for each value of y, any corresponding, all the corresponding x's for any given value of y have a normal distribution. For each value of y, all the corresponding x's have a normal distribution. As soon as we get into a regression model with 3 predictors and 1 outcome, now all of a sudden we've got into fourth dimensional space, and that's hard to sort of wrap our head around. The basic assumption of multivariate normality, again, each variable, so the univariate normality, and now all possible linear combinations of variables have a normal distribution. And again, thinking about this as an extension of bivariate, this bivariate normal distribution to sort of multidimensional space. Okay. This is difficult to test directly, but as we start to get into practical applications, we'll show you how we, if certain conditions are met, we're assuming that multivariate normality is at least a semi-tenable assumption. You're looking at me suspiciously.
No, I think I have a silly question.
No, it's not silly. What is it?
So if 2 variables are correlated, then we would expect multivariate normality. But if they're completely unrelated, we would expect the normal dome.
Yeah.
So
but that's still normal. That's still normal, right?
Right.
Even if they're orthogonal, right? That nice sort of sloping dome that goes out in a perfect circle, that's still normal, right? What happens if we start getting, and what we're going to test is looking at univariate distributions, and when we start getting univariate distributions that are incredibly skewed or weird, then that starts to throw off our various assumptions and things along those lines. And so difficult to test this directly in an efficient manner, but we've got some procedures that we'll go through and start to sort of think in whether or not we have violations to aspects of that multivariate normality. Now, many of our tests start to assume some level of robustness to violations historically, but as we start to get, and a lot of this is derived from increased computing power and being able to run really intense simulation studies under a number of different conditions, starting to question the extent to which some of these tests that we've tended to think about as being robust actually are robust. And when we're talking about robust, what does this mean? If I say a test is robust to violations of underlying assumptions, what does that mean, Sam? We should be finding what? In what? Proceeding. What do you mean? Because there's no, like, mathematics police going to come and kick down our door for running a test that violates assumptions. What's our concern if we violate assumptions? Okay, and so what are we using our results to glean? Inferences, right? Again, our inferences are predicated mathematically on us meeting these assumptions. And when we violate those assumptions, then sometimes that has some sort of systematic predictable impact on our inferences, sometimes it doesn't, right? But basically what it says is I'm saying, based on my results, that this is the relation between X and Y in the population. And that relation between X and Y, my data that I've collected suggests that that's some value that's reliably different than 0. But if I violated my assumptions, I no longer have confidence in that, right? And I no longer have confidence in the results of my test once I've violated assumptions. And so when we talk about tests being robust, we can say, yeah, we can have violations in our assumptions, but our inferences are still probably going to be relatively unaffected, right? But if it's not robust, and I start doing crazy stuff, right, then all of a sudden, who knows what's going to happen, right? So always make sure that we're going through testing our assumptions so that we're not just saying something that's probably not accurate because we haven't paid attention and have crazy outliers and non-normal data and weird stuff going on in our analyses. So for our distributional assumptions, some different assumptions, whether or not we're talking about grouped versus our ungrouped analyses. And so, Stephanie, this is getting into issue you brought up. Again, for our ungrouped data, right? For ungrouped data, our multivariate normality is assumed if each variable follows a normal distribution. So, if in my set, all of my predictors and all of my outcomes follow a reasonably normal distribution, and if my bivariate relations, if the relations between X and Y, all of my X's and all of my Y's are linear, so there's no nonlinearities in there, and they're homoscedastic, we're going to talk about what that means in just a moment. If, for say ungrouped data, for like regression analyses, if all my individual variables have a normal distribution, and all the bivariate, possible combinations of bivariate relations are linear in nature, and they're homoscedastic, then I'm going to assume that I've met my requirements for multivariate normality. Okay. Now for group data, normality assumption, again going back to stuff that we talked about before, starts to pertain primarily to the sampling distribution, I mean, not sort of the actual observed scores. Now, we still kind of have to be concerned about some of these other issues, but for repeated measure ANOVAs and some of these other things that we're working at with, primarily what we're going to be more interested in is having a large, appropriately large cell sizes to go through and take a look at stuff versus sort of necessarily our univariate distributions. We're still going to go through and we're going to test so that we know kind of what's going on, but once we go through, we can get a lay of the land in terms of if we have clear evidence of violating our assumptions of multivariate normality, then we can move forward and say, is this an issue, is it not an issue, that type of thing. All right, so review, distribution of sample means, right? Again, this is distribution of all possible samples that could be drawn from a given size from the population. Distribution of sample means, here, individual values are means. Based on our central limit theorem, we're saying that for any population with mean, mu, standard deviation, sigma, distribution of sample means for sample size n, will have a mean of this distribution of sample means that's equal to the population mean, and the standard deviation of this distribution will be equal to the population standard deviation divided by the number of people in each one of the sample. And as n starts to get increasingly large, that sample becomes very, very quickly normal. Okay? And again, this distribution of sample means starts to approach normality very quickly if whatever variable it is, whatever we're measuring, has a normal distribution of the population, or as our sample size starts to get 30-ish or higher, that very quickly starts to turn normal. Okay? Again, beat you guys over the head of this all last semester. People sort of feeling comfortable with this? Okay. Distribution of sample means. Distribution of sample means equal to the population mean. So if I have random samples of adult height and I know the population mean is 68 inches, if I run samples of 100, the mean of my distribution of sample means, or the expected value of the mean, is going to be equal to my population mean. I should expect that the mean of my distribution of sample means is going to be 68 inches. And again, this is a very large sample, so the distribution of sample means is going to become normal very quickly. What if I had samples of 15? Morgan, would that distribution of sample means be normal if I had sample size 15?
Usually it's normal over 30, right?
Well, yeah. So I don't have 100. So, but I only have I have a small sample. Should I expect my distribution of sample means of height to be normal with a small sample?
Oh, sample means? Yeah.
Yeah. Why?
Because their means not usual.
Yeah, and so what's the distribution of height in the population? Normal, right? So even if I have a small sample, even if the individual samples are small, because the outcome that I'm looking at has a normal distribution, I would still expect the distribution of sample means to approach normality quite quickly, because what I'm actually measuring has a normal distribution, right? But even if I'm looking at heroin use, monthly heroin use out there in the world, if I have samples of 500, distribution of sample means is going to start to become normal very quickly, even though what I'm measuring is severely skewed because I have a very large sample with this, right? So this is our measure of central tendency and variability, standard error. Okay, I was going to pick on someone. Tell me what a standard error is. Hopefully you all know what a standard error is at this point. Standard error, remember, this is the standard deviation of the sampling distribution, right? Standard deviation of standard error of the means, the standard deviation of the sample distribution of means, calculated standard error as, at least for mean, as the population standard deviation over the square root of your sample size. Again, if we think about this, standard error of the mean for sampling distribution of adult height, assuming a population standard deviation of 6 inches, 6 inches divided by the square root of 100 is going to give us a standard error of 0.6. Okay, someone give me a sort of conceptual interpretation of this standard error right here. What do you think, or what do you think, Alex? I say standard error of this distribution is 0.6. What does that tell me? So there's a couple ways we could think about this, right? So I say the standard error here is 0.6. And so what does that tell me about repeated measures within the context of this
sampling distribution. What do you think, Alex?
Can you say that again?
Okay, so I know that my standard error is 0.6, right? So what does this tell me about repeated samples of height drawn from the sort of population of adults?
That it's 6 inches. Above what the one sample is from the other.
Okay, close. Can someone help her out? Yeah. So I just want reinforced, because it's been a sort of a while since last semester. So wanting you to get a conceptual understanding of standard error, right? So how do we interpret standard error within the context of this example?
So depending on the mean of the obtained sample, it would tell us how many standard deviations away from the population mean we would expect it to be.
Okay, close. What we're saying here, we could interpret this as a number of different ways. We could say, based on the standard error of 0.6 with samples of 100, right, that I would expect any randomly selected sample of size 100 to be not 6 inches, 0.6 inches, a little over ½ an inch from the true population mean. Okay, that's pretty good, right? I'm expecting any random sample of 100 people that I would gather, assuming that I'm pulling a randomly selected sample. On average, I'm expecting sort of the sample that I get to be about ½ an inch away from the mean of my sample to be about ½ an inch away from the true population sample. That's pretty good, right? I could also say that I would expect any 2 randomly selected samples of 100 that I would draw. Again, if we're drawing at random from the population, I would expect that any 2 randomly selected samples to only be about ½ an inch away from one another in terms of their means. Right? I could talk about this in terms of how well my sample of 100 is representative of the population mean. Is my sample of 100 a good measure of the estimate of the population mean? If my standard error is 0.6? And John, you're shaking your head, yeah, why?
6 with respect to height is
It's pretty
very
close,
small.
right? We're a little over ½ an inch of difference, right? And so in this, we can look at this standard error because we're working with the units that are meaningful, right? And so if we calculate the standard error, thinking about the standard error is the standard deviation of our sampling distribution for sample size equal 100, we're doing really good here, right? So if I get a truly random sample of adults and I see the size 100, I'm pretty confident that this is a good estimate of people's actual height, right? Now, does it have to be 0.6 away? No, right? It could be way out here, right? I could get average height of people as 6'4". That's going to be a very infrequent sample, right? It's not going to happen a whole lot, but it's in there. It's possible, right? But in general, I'm expecting, on average, any randomly selected sample that I'm going to get is going to be probably about a little over ½ an inch from the true population mean. Any 2 randomly selected samples are going to be about a little over ½ an inch from one another, right? And in general, thinking about at this standard error, any randomly selected sample of height of 100 people that I pull is going to be pretty close to sort of my actual true population mean. Okay. So does this help sort of sinking sort of standard error back into place in terms of what we're talking about? Again, standard error being the standard deviation of our distribution of, in this case, means, but in any situation, standard deviation is the sampling distribution of any type of coefficient that we're calculating. Questions about this? Standard errors, if you can imagine such a thing, are going to become incredibly important this semester, because this is where when we have violations of assumptions, this is what it impacts. It impacts our standard errors, right? And if it impacts our standard errors, what is that going to impact? What do we use our standard errors to calculate? What do you think, Katie? Our confidence intervals, absolutely, and what else? That are related to our confidence intervals, kind of. Our inferential tests, right, our test statistics, right? We're not just calculating confidence intervals for the hey-ho heck of it, right? Just because we like to have them sort of sitting there and look at them. These are instrumental, so our entire method of inferential statistics is predicated on having some reasonable estimate of your standard error, right? And so if our standard errors are all screwed up and not good, then that screws up our inferential tests, and then that starts to have impact on our inferences, right? Because my standard error is either too big, it's too small, making my statistical test too conservative or too liberal, and so my conclusions start to become thrown out of whack because my standard errors start to become biased. Okay. So, review, but it is sort of one of those things you could review time and time again, and sort of starts to stick a little bit more every time you go through and review it. People are sort of feeling sort of comfortable sort of bringing some of this stuff back. Cool. All right. Univariate normality, talking about skew and kurtosis. Okay. Skew, third population moment. Mean being your first population moment. Variance, your second. Skew is your third, right? Skew is telling us about the symmetry of distribution. If we have positive skews, we have tails heading sort of larger values. Negative skew, tail heading towards lower values. Anytime we have a skew distribution, mode is going to be to the far side of the tail. Mean is going to be dragged out to the tail, and our median is going to be. Are you okay?
Yeah, I just got over the.
What's that?
I was just too fast.
Oh, okay. Oh, no worries, no worries. Happens to me too sometimes.
And it's fall over, so we're good.
Okay. Is the excitement of skew was too much. It was too much. We got so excited. I have to take a break. Too intense. Talking about skew. All right. So means always dragging out towards the tail, right? Mode going to be there towards the hump of the distribution. Median is going to be your measure of central tendency with that skew distribution here. Okay. Again, when we have a skewed distribution, particularly if the skew is quite severe, our mean is no longer a valid measure of central tendency. Mean is going to be drugged farther out towards that tail. Depending on our sample size and the degree of the skew, that's going to start to become more and more of a problem, right? And so when we're working through screenings, you know, it would be nice to say, oh, under this condition and with this number, sort of this is when it's a problem and it's not, but we can't tell that, right? You're going to have to think about how many people do I have in the sample, because you can have a wildly skewed distribution, but if you've got a whole lot of people, that tail might not drag that mean out too much if you've got a bunch of people anchoring it right there towards the middle, right? But if you have a sample of 20 and the same degree of skew, that's going to screw that up way bad, right? And so wanting to think about, take these types of things into consideration. So mode being on the far right or left, depending on the skew, median then being the middle value, which is why we go through and start working with transforms. When we're working with transform data, we're no longer looking at mean differences, we're looking at median differences. We'll talk about some of the consequences of transforms in just a moment. Okay. Kurtosis, fourth population moment, looking at peaks and shoulders. Okay. My concern, Angeline, when you're talking about a domed distribution and univariate normal or bivariate normal distribution when there is no relation between X and Y. When you said domed, I was thinking about sort of negative platyperic, right, which isn't quite, so we still got that same type of thing here. But this, in my mind, was sort of the distribution I had in mind, sort of this box distribution. If you see a square distribution, that's a good example of a negative kurtosis. All values are all occurring at about the same frequency, and then everything drops down. Positive kurtosis, leptokurtic distribution. This is where we have very, very peaked, and then kind of these flat tails. When we're thinking about flat tails, so I've got something if this is my X and Y, I've got something that goes, so this is kind of going down here. Look at that. Okay, never mind, I don't need to fool around with this.
No, stop.
Never mind. What's up?
Wow. Technology.
Oh, I was like, oh, they draw that, oh, that's cool.
Yeah, you can draw.
No.
Oh.
Okay, now you've got more important things to talk about. We'll figure that out later. All right, so,
It's a lot easier to see.
positive, negative choices. Remember that, is it moving? Is it doing? Stop.
It's like, oh my God.
Remember that our cartographic distributions tend to underestimate population variance, okay, for different reasons. For our negative kurtosis, we're missing those shoulders, right? Everything's, I mean, we've got these tails that are kind of extending out, that are sort of picking up some of it, but we're kind of missing that middle part where all sort of there's supposed to be a wealth of scores, and so we're underestimating variance here. Obviously, with negative kurtosis, we've got kind of got this domed peak. We've got too much in the shoulders, but we're missing those tails. So in general, we're concerned with kurtotic distributions that we're underestimating true population variance, and then that's going to be problematic a lot of times for our regression-based analyses. Yeah, Sam.
So for the dome-shaped one,
Uh-huh.
are we also underestimating like the peak? Because I see like the little highlight in the background. That
Yeah.
Yeah.
Well, this isn't contributing to underestimation of variance a whole lot because this stuff is, there's not a lot of we're not missing variability here because that's the peak where everything's sort of all collected anyway, right? We're worried about variances, sort of how spread out scores are. So yeah, we're not getting as many scores maybe in that middle as we should because we've kind of got this square distribution. That's less of a concern for why we're underestimating variance as opposed to sort of the stuff out there in the tails. People sort of familiar back on track with kurtosis? Okay. So looking at our skew and kurtosis, looking at our absolute value, our indices, but our associated significance tests aren't terribly useful. Why is this? What do you think, Lauren? Why don't we put too much faith in our statistical tests of skew and kurtosis? Remember?
Does it have to do something with the mean?
Kind of. With any general statistical test, what are we testing? What's the value we're testing against? What's the hypothesized value under the null for almost all of our statistical
All of them
tests?
the same.
What's that?
They're the same.
That they're what's the actual value?
0.
0, right? And are we assuming, do we need to have our skew and kurtosis equal to 0 if we're going to run our tests? No, right? And so it ends up happening, and so should we in general have larger samples or smaller samples? And if we have larger samples, what does that do to the sensitivity of our tests? It increases them, right? So I've got a good sample for regression, right? I've got 300 people, and I run my statistical test of skew and kurtosis, and I find that I've got statistically significant kurtosis, and I've got statistically significant skew, and I say, oh dear, and I look at my skew and kurtosis values, and they're 0.2 and 0.3, right? And so then I proceed to execute some ridiculous transform to reduce my skew and kurtosis because they're statistically significant. Did I need to do that? No, I've just created a giant pain in my own ass because now I'm not actually running effects with actual variables that are interpretable that mean something. I'm running an analysis because I had a statistical test that told me that something was statistically significant when I would expect it to be because it was a sensitive test and I don't need it to be 0 anyway, right? And so that's the problem. And you'll run into this. People like, I'm statistically significant skew, and so I transformed this. And so now I don't have variables that actually mean anything. And everything got a lot more complicated because I did something that I thought was helpful when it wasn't, right? So wanting to look at our absolute values Skew and kurtosis less than 2, you often see this as benchmarks for something that's normal, right? But as skew gets larger, your histograms will start to look increasingly wonky. Skew of 1 still looks pretty skewed when we run our histograms, right? Kurtosis values, again, this is Klein has a reference saying, you know, if you got kurtosis of less than 8 as approximating univariate normality with large enough samples, this is a hard package to sell to reviewers if you're like, oh, my data is approximately univariate normal because I have skew kurtosis kurtosis values of 7. But again, sort of with this thing, what we're really trying to demonstrate is that we don't have severe non-normality, right? We usually talk about like, oh, this is approximating normality. What we're really saying is that it's just not radically non-normal enough to cause a problem, okay? But again, what we're doing, if we go through and take a look, have people read this screening chapter in PSYC and Fidel? Do it. It's very good. I mean, it goes through this is the screening procedures for multivariate stuff, all based on PSYC and Fidel stuff. Work through that chapter, read it. It's going to be very helpful. And PSYC and Fidel talk about sort of the main problem we're concerned about with particularly kurtosis is that we're underestimating variability. We need variability in order to demonstrate correlations. But PSYC and Fidel is saying if we have positive kurtosis, generally, if we have samples above 100, we start to not have that much concern about negative or positive kurtosis. If we have samples above 200, we start to become increasingly less worried about negative kurtosis, right? So even if I've got a distribution and it's very square, right? And I've got a kurtosis value of -6, right? That's certainly something I want to make. So I'm going to flag in terms of my screening. But if I've got 250 people in there, I'm going to say, yeah, it's not great, but I'm probably not thinking it's going to have a huge impact on my inferences. And so, as with most of our screening, our stuff is, yeah, it's not great, but sort of luckily, I don't think it's going to screw up my inferences a whole lot. So again, in addition to our absolute indices, always going to want to run histograms, box and whisker plots, sort of take a look at what our data are actually looking at. We can have variables that we can say, oh, they're approximating normality because skew and kurtosis values were less than 2, and you guys know this. Then you pull up and look at your actual histograms. Any of that variable, the skew value of 1.5 looks very, very skewed when you pull it up, right? And so wanting to take a look and think about these things and sort of making a determination on whether or not this is problematic for my analysis or not. Questions on skew kurtosis, taking a look at that? All right, for our group-based analyses, again, this is literally a slide that's sort of a cut and paste from last semester, but just again as a reminder, generally thinking about our group-based analyses, robust violations of univariate normality, if we've got reasonably large sample sizes, some work done in the 60s saying even if we have about 25 people per cell, we can tolerate some pretty nasty univariate distributions because again, our assumption is the univariate sample or distribution of sample means is normal, not the actual observed mean that we're getting. But remember that we're not robust when we start doubling down on violations. So if we've got our groups have different shape and different variance. So if I've got group A, condition A, my scores have a very, very strong positive skew. And group B, my scores have a very strong negative skew. And I violated homogeneity of variance, then I've got problems, right? If I've got 20 people in this cell and 70 people in this cell, and I've violated homogeneity of variance, that's also problematic. And here, we've got systematic effects on our on estimation of our pooled variance that we can accommodate and sort of, or at least sort of know what's probably going to happen. If my larger sample has a larger variance, I'm going to overestimate the variance, which is going to overestimate my standard deviation, which is going to make my test statistics which is going to overestimate my standard error, which is going to make my test statistics too high or too small, and so I've got a conservative test, right? I'm not going to be able to claim statistical significance as often as I should. If things are going the other way, I've got a sample of 100 and a sample of 20, and my sample of 100 has much smaller variability than my sample of 20. I'm going to have too liberal a test. I'm going to underestimate the variance. My standard errors are going to be too small, which is going to make my test statistics too large. So I'm going to say that there's differences when there's actually probably not, right? So this is where, when we're going through and screening our data, not just saying, yeah, this is a problem. In many cases, we're able to say exactly what this problem is likely to be, and then when we go through and we're making interpretations on our results, we can take that into account, right? So let's say I violated homogeneity of variance, and my larger sample has a much larger variance than my smaller sample, and then I run up in my primary analyses, I find an effect of p equals 0.06, right? Well, then I might say, it's like, well, we've got this violation that I know is going to give me too conservative of a test. We're kind of borderline right here, so one hypothesis might be that this is actually sort of my violation is actually giving me too stringent of a test, and so that's why I'm getting sort of this marginal effect when I was hoping to get something that was statistically reliable, right? And sort of trying to put all these pieces and parts together to be able to start to predict what's going on with our stuff. Small sample sizes, violations of normality, that's always going to be a problem, okay? So again, taking that stuff that we talked about last semester, applying it to the stuff that we're doing here, a lot of the same principles still apply. Questions on any of that right now? Or I'm assuming you're adjusting your hair and not having questions, okay?
I think, yeah, you're probably used to that too.
Okay.
Adjusting your hair.
Right. Yeah, I know, just a lot of, make sure my beard's in the right place. Outliers, talked about univariate outliers. Extreme values given on a variable, so univariate outliers, we've talked about this a lot. What we haven't talked about really is multivariate outliers. Multivariate outliers, this is going to involve configurations of scores that are weird, okay? Individually, the scores might be fine, but when we put them all together, they start getting funky, okay? So let's say that I'm looking at an example where I have age in years, income in dollars, and region in terms of geographical location in the United States. I can have someone who's 10 years old. It's going to fall within the normal distribution of age. Someone, if I have a truly representative sample of people in the United States, someone who's 10 is not odd, right? They're kind of right there where we would expect. Someone earning $130,000, that's fine. That's not going to be weird. We have someone residing in the rural South, that's fine, right? But if we start combining these together and get a 10-year-old person who's making $130,000 a year residing in the rural South, all of a sudden, that's a weird case, right? And this is the principle of a multivariate outlier. Individually, we might not see anything going on, right? All of our values, we have no outliers in our univariate distributions, but as soon as we put all those variables together, we've got someone hanging out in weird space that we need to account for. Possible causes of our outliers, incorrect data entry, right? Always want to go through and make sure that we haven't had someone add an extra zero to something and it's caused a funky score. I do this all the time. Forget to tell SPSS that 999 means a missing value, and now I've got a very interesting mean, and sort of my histogram looks pretty funky. It's got like one column here and then someone, way out there on the end. This is important. Think about cases not a member of the intended population of study, right? I've gone through and I'm looking at income among freshmen, right? And I go through and I find sort of most freshmen are poor as freshmen want to be. But then I've got someone who's reporting making $80,000 a year, right? This could be a non-traditional student who is already set up, right, and is coming back. And I might say, fine, $80,000 is a reasonable income for this person, but this person isn't who I'm studying. I'm interested in 18, 19-year-olds, and I got a 40-year-old that snuck into the sample who is a freshman, but they're not the type of freshman I'm looking at, right? And so wanting to go through and look at your data and say, is this person a member of the population of interest? If they're not, we can go through and exclude that person without too much, actually, we're improving our inferences if we get them out of the way because they're not a member of the intended population. But sometimes our outliers are attributable to people who are members of the intended population, but we're just getting underestimation of the population variability as a consequence of our sample, right? So I go through and I calculate some, I'm looking at, say, alcohol use in the population, right? And so most people are maybe reporting, you know, X number of drinks a day, or they're drinking some, and it's sort of in the middle. Yeah, but it's a small sample. Then we have someone way out, sort of that's out there in the sort of on the high end, right? Now, if I'm running a sample of like 20, 25 people, and most people are kind of out there, but then this person is way out there. Well, people who use alcohol heavily, maybe part of my population of interest is just my sample hasn't captured some of those people who are far out there. And so I shouldn't be terribly surprised that maybe sometimes I catch someone out there on the tail, even when everybody else is kind of packed in amongst one another, okay? And so, and then also if I'm going through and I'm even getting very large samples, I'm going to expect to have some people capture those people out there on the means, right? If we're thinking about looking at people's height, right? And I have a very large sample, I'm probably going to get some people who are very, very small, and we get people who are very, very tall, right? I'm probably going to capture them, and so those people might still register as a univariate outlier. And so even though they're outliers, they're still people who are part of my intended population. But if I've got a large sample, hopefully I've got a large enough sample that's robust, right? So that person who's an adult who's 4'8", and the adult who's 6'10", in a sample of 250 people aren't going to be enough individually to start throwing my mean too far around. And so even though they're outliers, I can say I'm still going to tolerate those individuals because they're probably not going to pull start moving my mean around too much. But particularly in small samples, when we start worrying about things, possible consequences of our outlying values, influence on our estimates of our coefficients. If we're looking at means, that starts dragging things around, right? And we don't want that. Inflation of both type 1 and type 2 errors, right? So this is sort of confusing. It can make our, sort of make us say we have differences when we don't have differences too much. We can make us say we don't have differences when we do have differences too much. Outlying values are problematic. And then starting to reduce the generalizability of our solution. If we keep that guy, that 40-year-old guy who's making $80,000 a year in our sample of freshman income, if we get a couple of those people in there, we're going to have a solution that doesn't actually generalize the population of interest because we've got weird people in there that shouldn't be in there. Okay. Questions about outliers? So this is when we're going through and taking a look, and again, and I've said this before, we're kind of lucky in psychology because I kind of have arbitrary caps on our measurement, right? Like, so you can't, you're not allowed to have a BDI score of 10,000, right? You can't have an extroversion score of, 400 just because there's only so high you can be, right? This starts to become problematic if we're looking at like epidemiological stuff, things like business and e-com, where you can have someone who is a multimillionaire in your sample of Laramie, and so all of a sudden you got people sort of dragging your mean estimates all over the place, right? It's less of an issue in psychological science, but still something to start to think about and be aware of. So identification of univariate outliers. Again, pay attention to your dichotomous variables, okay? Dichotomous variables with huge splits, 9 to 1, these are outliers even though there's only 2 values that they can take, right? They're not super extreme. You've just got an incredibly unbalanced variable in there, and you need to start thinking about what you're going to do with that, right? So cases in the small category sort of exert undue influence, right? So the one person, so I'm looking at my sample and I've got 90 women and 10 men, right? Those 10 men have a much stronger influence on sort of the outcome than the 90 women do, right? So we've got people in the small category having undue influence. When we have these extreme splits, it makes our relations between gender and whatever else we're looking at, it starts to attenuate those. It makes them look smaller than they probably are in the population. And unless, when you run into variables that are having these ridiculous splits like this, unless it's absolutely central for you to have in your analyses, think about scrapping it, right? Because in that situation, gender is probably not something that you can reasonably examine with any type of confidence in your data because you don't have enough, right? There's another issue when it comes into looking at sort of diversity issues in psychological science. Our samples are overwhelmingly white, and so what we do instead is then group everybody who's not in the majority category all together and call them other. Well, still that might be 90% in the majority group and 10% in the minority group. And one, we're not getting any good estimates off of anything. Two, we can't draw any sort of conclusion by just grouping everybody else into another category. And so unless it's very essential that you take a look at ethnicity, culture, race as a variable in this, think about just not worrying about it at all, right? And if ethnicity, culture, and race was something that was central to what you're looking at, you should have done a better job of trying to get a more diverse sample in the first place. You should have thought ahead and recognized that this was going to be an issue, right? So again, when we run into these dichotomous outliers, always be aware of making sure you're taking that into account. Outliers on our continuous variables. These are variables having extreme scores. Generally large samples will set a value of 3.29. But again, remember that this isn't like a cut and dry thing, right? If we get values that are pretty close in either direction, those are maybe things to look at. It's not like, oh, this wasn't an outlier at 3.28 and then it hit 3.29 and now it was, right? But these standardizer scores may start to help going through in your write-ups for your screening. Make sure you're telling me what you're using as your criterion for an outlier in that situation, okay? And again, note, when we start to get large samples, it's almost certain you're going to have extreme scores, right? If you have a sample of 300, 400 people, there's going to be some people out there on the edges, right? And that's just telling you you've got a large enough score to capture some of that broader variability. These aren't things to freak out about. It's something to go through and take a look and think about what you're measuring, right? If I'm measuring some natural or some existing characteristic in the population and I get someone who's very, very high and very, very low, I should kind of expect that, right? Maybe I don't do anything with it. But if I'm looking at something like reaction time and I've got someone who took 4 minutes to react to something, maybe I say, we're going to go ahead and get rid of that person because they're probably they haven't responded to my manipulation as I wanted them to, so we're going to go through and get those out. So again, think about as you're running your screening, what are we trying to measure? What were the methods that we used? Why might this person be hanging out on the margins? Does it make sense to include them? If I do, what are the consequences? Should I get rid of them? What are the consequences of that? Okay. Box and whisker plots. Again, I'll review. Midline is the median. Remember, the box and whiskers are median based statistics. Bounds of your box are your first and your third quartiles. Your interquartile range is your boundaries of the box. Whiskers are your interfits. Minimum and maximum values in the distribution, or if we get values that are beyond 1.5 times the interquartile range, our whiskers go to the most extreme value that's still within 1.5 times the interquartile range. Values that fall outside of that, indicated in asterisks, outside of 1.5 times the interquartile range, we get asterisks. These are things that are falling 3 times the interquartile range, wanting to go through and be able to sort of identify components of your box and whisker plots. Remember that we have a relatively normal distribution. If we got relatively symmetrical box and whiskers, about 95% of your data should fall between the whiskers. Okay. But again, this is based on median-based statistics, so you want to make sure that you're not identifying these as means and standard deviations and things like that. Okay. How do we address univariate outliers? One, always make sure they're real scores. If they're real scores, if they're not real scores, just go through and fix it. That's easy. Consider the possibility of problematic variable, right? So I'm going to go through and I'm going to look at substance use in my sample, and so I'm looking at alcohol use and stimulant use and opiate use and cocaine use, and all of a sudden I find that for stimulant, alcohol, and sort of pain pills were fine, but then sort of cocaine's a little exotic for my sample and it looks really kind of skewed and weird. Do I need to include that in there? Because if I do, I'm going to have to do a bunch of stuff, and unless it's central to what I'm trying to look at, I might think about excluding that and just saying, we didn't get enough people who were reporting this type of behavior in order to make that worthwhile throwing it in the mix. We're just going to get rid of it. But if it is central, looking at whether or not our individual outliers are part of our population of interest, right? Is this someone who is not who I'm trying to study? If not, I can get rid of that person. If I can make a case for not just, oh, this person was had a large value, and so they're not who I'm looking at. If you go through and take a look at your data and you can say, all right, this is someone who came in and was clearly not paying attention to the manipulation, that's not who I'm looking at, so I'm going to get rid of that person. Or this is a 40-year-old freshman, I'm not interested in looking at that person, right? And so going through, if you can make that case, you can get rid of those people without loss of generalizability. But if you've got an extreme case, and it is part of the population of population of interest, and it's an actual true value, and you can't really justify throwing it out, what we can do, and this is common practice, hopefully this isn't a lot of data. You don't want to do this a whole lot, but smoothing procedures, right? One of the most common smoothing procedure is to take that outlying score with a value 1 unit larger than the next largest score, right? So I've got someone who is in sort of my marijuana use in my sample of 30, so we've got some reasonable, and then I caught someone who was just really high on the end there, and I'm saying, yeah, they're a college student, and this is just a heavy user. We didn't get a lot of heavy users in here. And so what I'm going to do is I'm going to take that person's score and I'm going to set it adjacent, 1 unit higher than the next highest value in. So I'm just taking it and kind of bringing that person in. They're still representing in sort of rank order as the highest value user in my sample. I'm just trying to mitigate the potential impact in this smaller sample that I have. I'm not just going to throw them out because these are actually maybe the kind of people I actually want to look at, right? So throwing out people who are the people of actual interest doesn't make any sense, but I can't just let that data sit as it lies because it's going to screw up my analysis, so I'm going to try and smooth this in, right? Other thing we can do, and particularly for things like substance use, reaction time, other things like that, often very common in the literature for transformation. This is just what everybody does. It's known within this area that this is a variable that has a tremendous skew to it, things like reaction times particularly, right? And so what we're just going to do, alcohol use oftentimes is one of those things, we're just going to use transform scores. If you weren't using transform scores, you would be a weird person. And so the first thing your reviewers are going to say is, why aren't you transforming that? Everybody transforms, right? And so thinking about convention within your area and potentially using some transforms to try and create a new variable that's not your original variable. Always remember it's not your original variable you're working with. You're working with a transform variable where we can start to execute these transformations to start to bring things in line. Okay. Questions about these? All right. Again, important to go through and address your univariate outliers before you start screaming multivariate outliers. You don't do something with your univariate outliers first. Those cases that are coming up as univariate outliers are also going to pop up as your multivariate outliers. It ends up being redundant, so make sure that you're addressing any univariate. If you're going to do something with the univariate outlier, make sure that you do it before proceeding on to the multivariate multivariate outlier test. Okay. You'll also see people, it's not, trimmed means, right? People will use in some literatures, and there's good statistical justification for, particularly if you've got large samples or certain types of research, people are reporting trimmed means and standard deviations. That's saying that for my sample, I'm just going to go through and I'm going to take the top 5% of scores or 10% of scores, and I'm going to remove those. I'm going to take the bottom 10%, I'm going to remove those. So I'm getting a nice estimate of the people kind of right here in the middle 90%. Now, depending on your trimming procedure, you can lose a lot of data that way. But this is another thing you may see within the literature, people reporting trimming means and things along those lines. Okay. So if we're talking about transformations, some things you need to think about before you decide to execute a transformation. Thinking about data-driven analyses versus theory-driven analyses. If all I'm interested is a data-driven analysis, if all I want to do is demonstrate relation between X and Y, or some variation of X and Y, then transformation, the decision to transform isn't really a big deal, right? All I want to do is describe the relation between these two things, then it doesn't matter if I'm talking about the relation between X and Y or the relation between X and the log transform of Y, who cares, right? But for what we're doing, and so like if we were running like a model that was based purely on prediction, I want to just predict this outcome. I could care less what the actual values are, what the values mean. I'm just trying to maximize my prediction of this thing. That's completely data-driven. I don't care what the inputs are or how they get screwed around. Then transformation is not a big deal, right? But that's generally not the type of research that we're doing in psychological science. Generally, we're trying to understand how some phenomenon relates to another phenomenon, and when we start transforming things, then that starts to get more complicated to interpret those relations. We're no longer working with the relation between X and Y, we're working with the relation between X and the log transform of Y. And sometimes people will conveniently try and forget and omit the fact that they've log transformed Y. But as soon as you log transform Y, it's incumbent on you to make sure that people in all of your interpretations know that we're not talking about Y anymore, we're talking about the log transform of Y, right? And so I have a general sense for some of the measures that we use in general. I know what sort of a score on sort of this measure means, but as soon as you start talking about the log transform of that measure, I don't know what that means. I don't have a good sense for how that relates to things. It seems that you've established a relation between X and the log transform of this score. I just don't have a good sense of what that means for practical purposes, right? So something to think about. And again, as I said, in some areas, necessary common practice to transform scores. Sometimes in some types of studies, it'll be strange if you don't, right? But what you always want to do is make sure that you have sufficient justification for any type of transform. You don't just transform just for the hey-ho heck of it. You want to be able to say, this was the reason we needed to execute a transform on this variable in order to bring it in line with stuff, or so that we could analyze it reasonably, so on and so forth. Okay? Tabach and Fidel, if you read through that screening chapter, they're all right with transformation. Come from a training background where let's not do it if you don't have to, because it just complicates interpretations, right? And then I have to go, it's also, interpretations are a mouthful without, instead of just saying BDI score, the log transform of BDI score every time you bring up BDI score. So try and have a justification and use this in cases where other types of approaches are going to be not advantageous for obvious reasons. Common transforms. This is based on, again, Tabach and Fidel. A moderate positive skew, you take a square root transform, large positive skew. Here, I've got log transforms. In general, if you're going to conduct logarithm transforms, use base C, so natural log. Natural log actually has, and when we get into regression stuff, natural log has some desirable probabilities in terms of interpretation that make it nice. So, and the log transform of X and the natural log transform of X are going to give you the exact same distribution. The values will just be different.
Log transform of x, thinking about if we have a large positive skew where 0 is a value on our scale, we're going to want to add to our, whatever our variable is, we're going to add a constant to that. Why do we need to add a constant if we have zeros in our natural scale? You jump way back into high school algebra class. What happens if we try and take a natural log of 0? Doesn't give us anything. It's an undefined, right? You can't take a natural log of 0, so you just get blank values, right? So what we need to do in terms of choosing your constant here is choose a constant such that the smallest value is equal to 1, right? So if my scale goes from 0 to 100, what's the constant that I should use, Stephanie?
I'm sorry,
If my scale goes from 0 to 100, what's the constant I should add on to my 1? What if it's -5 to 100? 6, right? So so that first, the smallest value be equal 1. I mean, at this stage of the game, it's all arbitrary. It doesn't matter. You could make the constant be 1,060 if you wanted to. It doesn't make a difference. But in general, sort of trying to stay consistent there. Severe positive skew, inverse transform is something that you can use. So this is just taking 1 over all of your values. So if you just say compute inverse x and say 1 divided by your variable name, that's going to go through and switch things around. Now when you, and if you have like a various kind of L-shaped distribution, you can take x plus your constant with 0 values, again, because you can't take the inverse of 0, right? So you need to adjust for that, otherwise you get a bunch of missing values. When we start getting into negative skew, this is where things get kind of crazy, because if you have a negative variable and you don't account for the fact that it's negative, you got a negative skew, and you just try and say take a log transform of that, it's just going to make that skew worse. Okay, so what we need to do is inverse the skew, the variable, to flip it around. So I've got a negative skew. What I need to do is I need to take my variable and subtract it from some constant k, so that now all my very smallest values are now large values, and my large values are now small values. So basically what I'm doing for this skew is I'm taking my negative skew, creating a new variable that turns it into a positive skew in my reflected value, and then take the square root, the natural log inverse of that, okay? And so typically we'll choose this inversion constant as equal to the largest score in the distribution plus 1, right? So if I've got a negative skew where all my values are 100 and then they skew down to 0, what I need to do is reflect that to make it a positive. So now I'm going to take 101, subtract all my 100. So now everybody who had a really high score of 100 now has a value of 1. Everybody with a real small score now has a large value. And so now we flip things around, and so now we can then implement the transform that kind of brings things into line. But now in terms of our interpretation, negative correlations now mean positive correlations. And so you got to keep all that stuff in your head so that you're communicating things effectively. Questions on any of this? All right. So interpretation of our transform data, I mentioned this before. Anytime we start working with transformed data, we're making interpretations on associations with the transformed variable, right? It's not whatever outcome we were looking at before, it's a transformed outcome. And so we have to make sure that we're communicating that effectively in our write-ups. So again, if I log transform regression scores, I'm not looking at the relation between regression or extroversion and regression. I'm looking at the relation between extroversion and the log transform of regression. Now, I might have known what the aggression scale was, but log transform of regression starts to get harder to understand, right? So it just complicates your interpretation. So this is why you should
use these types of things judiciously. Now, if we're looking at grouped data, we're talking about differences in medians with groups as opposed to differences in means, right? So we're running a means-based analysis, but when we transform our data, we're no longer working with means, we're working with medians, okay? What happens is our transform changes the shape of the distribution, but not the order of scores, okay? So if I have a very skewed distribution, right, and I run a natural log transform on it, it's going to change the shape of that distribution because that's what the transform is supposed to do, right? It's going to bring everything in so we don't have a huge skew. But for that data set, in that skewed set, the person who's the median value, the person who's exactly the middle score with, if it's a sample of 101, the 50 scores above are still the same 50 scores above in the same order, and the 50 scores below are still 50 scores below in the same order. We're just kind of bringing them in and straighten them out. So the cases at the median of the transform variable is going to be the same case at the median of the untransformed variable. We're just changing the distribution of the actual scores. So, and this, this is about polyandrous live-bearing fish that I found off the internet, which I thought was interesting. But if we take a look at, I don't know what they're looking at in polyandrous fish, but this is the distribution of whatever outcome that they were looking at, right? And so they decided that this was too skewed for them to use, so they transformed those data. But whatever value is right here at the median is also right here at the median of this. The same case is still the same value at the median. Median stays identical, so the value doesn't stay the same, the values change, right? But the person who's at the middle of the distribution remains the person at the middle of the distribution no matter what. It's just our means start to change around because we've changed the scaling of that variable to bring it in line. And people kind of get a sense for sort of what we're working with in terms of our transform variables here. Okay. This is a good stopping point. We'll sort of jump in with multivariate outliers next Wednesday. Okay? Cool. Any questions about anything we've covered up to this point? Feeling good about things? Okay. Cool. Awesome. Thanks.